So we've been looking into limits and solving limits, both looking at them graphically and algebraically. And we've looked at one-sided limits, looking at that graphically, but now we're going to look at this algebraically. And a lot of times in mathematics and applications, you have multiple equations that you're using to represent what's going on. It's not just one equation. Maybe after time, things slow down and you have another equation that represents it. And so you have what we call these piecewise equations. And we've graphed piecewise equations in algebra. So let's look at an example and let's look at solving limits algebraically, one-sided limits. And so let's say we're given that f of x is equal to 1 minus x squared if x does not equal 1, and the equation 2 if x is equal to 1. I'm sorry. Let me just see if that's, yeah. Okay, so basically, this actually, I guess it is a piecewise equation, but normally there's more like x is less than or equal to, or x is greater than these values. But so let's look at the following. So find the limit as x is approaching 1 from the left of f of x, and the limit as x is approaching 1 from the right of f of x. So how we're going to write this, we're going to look at the limit as x is approaching 1 from the left of f of x, and we're going to find the limit as x is approaching 1 from the right of f of x. Let's first talk about this graph, because I think that that's helpful, but we really don't need to have the graph in front of us to do this. If x is approaching 1 on the left, basically, if x is approaching 1 from on the left, I am using this equation 1 minus x squared for all values except for 1. And so I'm really looking at this piece of the equation as I'm coming in on the left. Basically, this is the picture of 1 minus x squared, graphing that. There's some open hole there at x equals 1, and then we have a point here at 1, 2. So basically, if I graph this, and if I think about back in algebra, we can use tools for shifting what graphs look like. So here, if I think of 1 minus x squared, I know there's so many things going on in calculus, and I want to kind of just review. So if we looked at this again, this might help it as negative x squared plus 1. We can think of graphing negative x squared. That's just a reflection of our graph, that negative in front across the y-axis. So that would look like this. So this would be y equals negative x squared. But that plus 1, recall that plus 1 shifts the graph up 1 unit. Okay, this is across the x-axis. And so if I looked at this, I would have shifted up 1. So my vertex, another way to think of this, because this is actually in vertex form. My vertex is at 0, 1. And then at 2, let's just be careful. We're going to have an open circle there on our graph. So I'm just curious at what 2 is. So if I plug in 2, wherever I saw an x, I'd have 1 minus 2 squared or 1 minus 4. So I'd have a point at 1, negative 3. So at 1, negative 3, I'm going to have an open circle. Okay, so that's just that graph of 1 minus x quantity squared. When x is not 1, oops, I'm sorry, I made a mistake. Can we just change this problem a little bit? Let's change this to x not equal to 2. And how about at x equals 2, we have 2. And I'm going to change this. We're going to approach 2 on the left and the right. Just makes it a little bit easier. Okay. So that what we just drew was the picture of 1 minus x squared when x was not 2. If x is 2, this function is telling me that my y value is going to be 2. So when x equals 2, I really have a y value of 2. I have a point here at 2, 2. So now if we look at this graphically, we can look at and do this. When we're looking at the limit as x is approaching 2 on the left-hand side, that means we're looking at the graph and we're coming in on the left-hand side of the graph. As we get closer and closer to 2, we're trying to figure out what is that y value that we're getting back. And if you look at it, well, remember we did direct substitution before, right? It's telling me I'm using this equation. So if I did not have this graph here, we could just do direct substitution, which would say 1 minus 2 quantity squared, because that's what I'm approaching. And then squared, which would give me 1 minus 4, which is -3, which I can see that also on the graph that my y value is -3. So that limit as x is approaching 2 on the left, showing it algebraically, I get -3, and showing it graphically, I get -3. And so same sort of idea. I'm going to look at this when I'm approaching this on the right. So I'm just going to move it down. So approaching it on the right. So these are values when x are greater than 2. Well, again, it tells me to use this equation. If x is greater than 2, I'm coming in on the right-hand side. Following the graph, I still, even though it's, remember we said if it's an open circle, that's okay. But we're looking at what is happening. What are we getting closer and closer to, which is still -3 graphically. And then algebraically, x not 2, x is greater than 2, we use this equation. So we can do our direct substitution again of 1 minus, we're approaching 2, so plug in 2 here, which again gives us -3. So then the next part of this question, it asked us, does the limit exist for as x approaches 2 of f of x? If so, why? If not, why not? Let's say this was part B. So part C, does the limit exist as x approaches 2 of f of x exist? Why or why not? So recall we talked about limits existing. A limit exists if the left-hand side limit equals the right-hand side limit. And both the left and the right are equal to each other. So we would say the limit exists. And the y is because the limit, again, as x approaches 2 on the left of f of x is equal to the limit as x approaches 2 from the right of f of x. And we could even go further and tell you what that limit is, right? We already found that. And so the limit as x approaches 2 of f of x is equal to our -3. Okay, so now we have another example of looking at a piecewise function. We have three separate equations, and it depends on the value of x. So for the first equation, we have the square root of 1 minus x squared all underneath the radical. And that's for values for x, where x is greater than or equal to 0, but less than 1. Our second equation of f of x is 1. And those are for values of x when x is greater than or equal to 1, but strictly less than 2. And then the third equation is x equals 2 when x equals 2. So notice where our domain is limited here. We don't have the domain from negative infinity to infinity. Those inequalities are telling us what our domain is. And so the first question is asking, what are our domain and range? And so I can tell by just looking at this what my domain is. And so notice here, I'm hitting all values from 0 to 1. If I look on the number line, I'm including 0 and I'm going all the way to 1, not including. And sometimes you write that without parentheses. If I look at my second equation, those are telling me my domain values, I'm starting at the value of 1. So I'm including it. So I'm going to put a bracket and I'm going to the value of 2, but I'm not including it. I have a parentheses. But that second piece, or I'm sorry, not the second piece, the third equation is when x is 2, I use 2. And so I'm using this value of x equals 2. So I'm actually closing that off because that's just for x equals 2. And so my domain, all the x values I'm using are from 0 to 2, including those bounds. So my domain is a set from 0 to 2. The range is a little bit harder because you kind of need to know what the graph is looking like, and you should be getting more and more familiar what your graphs are looking like by these equations. 1 minus x squared. Well, let's look at that. So if I had y equals 1 or minus x squared and the square root of that whole thing, notice if I square both sides of my equation, I would get y squared equals 1 minus x squared. And let's add x squared to both sides. And notice here I have x squared plus y squared equals 1. So maybe you recognize that. And notice that this is just a circle. It's centered, it's in that standard form of a circle, x squared plus y squared. The center is 0, 0. So this is with radius is equal to, I'm sorry, not radius. I can tell you, with a center 0, 0 and a radius. So remember this was equal to r squared. I don't know if you guys remember, I'm just going to put it up here. Standard form of a circle is x minus h quantity squared plus y minus k quantity squared equals r squared. Where center is equal to hk and radius is r. So our radius square root of 1 is 1. Then notice though that this is just the positive in here. So this is actually what we are looking at is just a semicircle. So this is a semicircle. And again, the y values we're always going to get back are positive. So it's a semicircle that's above the x-axis. I probably should have given myself more room before I wrote all that stuff. Okay, that's okay. So if I started just to draw that first piece from 0 to 1, that actually even limits it a little more, doesn't it? Because normally, like I said, first we would have a whole circle with a radius of 1. But then we limited it because of the square root, it was just positive. So if I got rid of what was below the x-axis, but this is just telling me my x values have to be between 0 and 1. And so if I look at when x is 0, it's actually starting here. So I need to get rid of this piece. Starting at 0, I have 0. And then at 1, I'm on the x-axis. And then if we look at what is between 1 and 2. Well, f of x is 1. So recall, if you have y equals a constant, that's just a horizontal line. Oops, I need to be a little bit careful on my inequalities, because notice that this is x has to be strictly less than 1 for my first equation. So I technically should have an open circle at this point, 1, 0. I'm just gonna, because x is greater than or equal to 0, I'm gonna put a solid circle here. So let's graph the equation y equals 1, which is just a horizontal line, but we're limited with our domain for when x is 1, we have y is 1, so we have a solid circle because it's x is greater than or equal to 1. Horizontal line until we get up to 2. But at 2, we're going to have an open circle. So that's what our second equation looks like. And then the last equation, it's only a point because it's for the value of when x equals 2. It tells me my y value is 2. So I know I have a point here at 2, 2. Okay, so recall range are all the y values your graph is hitting. And we have some jumps in here from what our graph is hitting for these y values. And so if I look at my range, all the y values I'm hitting, notice that smallest value, I'm getting really close, but don't include, is when y is 0. And then I have all the y values until I get to 1. So I'm having the y values not including, so interval notation, I'll have a open parentheses and 0, comma to 1 bracket. Because notice I do have a y value of 1. But notice there's no y values between 1 and 2. There's no value of x that would give me that y value. So I will put a union here, meaning I'm also including the y value. When y is 2, when x is 2, y is 2. So I do have a y value that I get back of 2, but that's just a single point. So how we can denote that is just by the set notation. So plus the set of the number 2. So limits existing. That is part B. But before I do that, any questions on part A? Finding the domain and range of our piecewise function. So question was about the range and about how I had written that we're also including that value when y equals 2. And so there's a couple of different ways that we could rewrite this notation. And unless they tell you what specific notation, I would take it anyway. But there's a couple different things that we can do here. So for like the range where it says our y values are between 0 and 1 and not including 0, but including 1. We could write that in inequality notation. So 0 is, the only thing you have to be careful is, so we're talking about y value for range. So 0 is less than y is less than or equal to 1. And, or actually we probably should put or, because if we're talking about sets and or mean different things, and means it has to, this has to occur and this has to occur. And really the cases are or statement union. Either y is bigger than 0 and less than or equal to 1, or y is going to equal 2. Either one of those cases is part of our range. So I could even get into more detail on how to write that, but let's just move on to the next part. And part B says, at what point C, if any, does the limit as x approach C of f of x exist? So if our domain is limited not from negative infinity to infinity, we can say that our limit exists actually for just one-sided limits. And so if I look at this, I can see that my value of C, any value of C, and that's my x value, any value between 0 and 1, not including 1, is going to exist. So if C is either between 0 and 1 and including 0, the limit exists. I think the better question this would have been is where, if any, does the limit not exist? And so the other values where it's going to exist is if I come in on 1, but not equal to 1. So if C is within this area, so if C is bigger than 1, it's bigger than 1, but less than 2, the limit also exists. So again, I think the better question is, when does the limit does not exist? So what values in the domain does the limit not exist? Sometimes looking at the trouble spots that you're going to occur, like sometimes when we're looking at the domain, what values we have to exclude, help us. And so if you look at this, this is where you're going to have any jumps in your graph. And so notice that in our graph, we have this jump, and we're going to talk about continuity, hopefully tomorrow. So notice we have a jump when x equals 1. We're getting really, really close. And let me just look at this, show you right now. If I looked at the limit as x is approaching 1 on the left. So if we were looking at our graph and coming into 1 on the left, what y value are we approaching? This is of f of x. Well, this y value that I'm approaching is 0. But if I go in here and I look at the limit as x is approaching 1 on the right, and so if I'm coming in on the right-hand side of 1, I'd be using this graph of y equals 1. And notice as I'm coming in, my y value is 1. And so right there, I can say that my limit as x approaches 1 on the left of f of x does not equal the limit as x approaches 1 on the right of f of x. So the limit doesn't exist when x equals 1. And maybe we should call it C, because that's what they were calling up here. Okay. Again, because of our domain being restrictive and not from negative infinity to infinity, it's okay for a limit to exist if it's endpoints of our domain. And so our limit does exist if we're approaching 1, x equals 0 on the left of this, we're approaching 1. I couldn't look on the right-hand side of x equals 0 because that's not part of our domain. If I look at the coming in on the left-hand side of 2, notice my limit still exists, even though that's not the point. But as I'm approaching 2 on the left, notice my y value is 1, even though that I have a point up here at 2, 2. So that limit is okay as I'm approaching 2 on the left. And that's the last piece of this was the questions. At what points does the left-hand limit exist, but not the right-hand limit? So left-hand limit exists if we're looking at that right-hand bound, right, of our domain. We can come in on the left of 2, but notice there's no value I can come in on the right because that's not part of my picture. And so at what point does the left-hand limit exist, but not the right-hand limit? That would be when x equals 2. So we can look at the limit as x approaches 2 on the left of f of x, but the limit as x approaches 2 from the right of f of x does not exist. X can't be greater than 2. Because it's not part of our domain. It's the same sort of reasoning. I'm sorry, this is shifts. For that last question. Oops. So I'm going to pull this down. So the last piece, it says what points does the right hand limit exist, but not the left hand limit? So right hand limit, we can approach x equals 0. If I approach x equals 0 on the right of this function, that's telling me that I'm getting back 1. But the limit as x approaches 0 from the left, there's no piece of the graph there. This is not part of our domain for anything less than 0. Does not exist. So we technically Really could have done all of this without the picture, except for really the range. The range was the only piece I was needed to kind of see what my graph looked at like to get that range. I guess also the other thing to think about is when we're looking at piecewise functions, it's really helpful to see what's happening on each side of a value of x where your graph is changing equations. Let's pull or talk about another question real quick. Okay, so our next example, I'm going to do this without graphing it and showing you how to do this algebraically. So we have another piecewise function. We're calling it f of x again. We have three equations. Our first equation is 3 minus x if x is strictly less than 2. Second equation is 2 if x is equal to 2. And the third equation is x over 2 if x is greater than 2. And we want to look at the limit here as x is approaching 2 from the left of f of x. So let's think about which equation we're using. And we can figure out which equation we're using by looking at what values of x you're plugging in. Well, if we're approaching x on the left-hand side, these are using values. We're going to use values of x that are smaller than 2. And so that tells me then I need to use equation 2 because this tells me when x is less than 2. So this tells me we need to use equation 2. And so I can do direct substitution again. So I can go in here and I'm going to look at using the first equation. And so I can do 3 minus, I'm going to put a parentheses wherever I see an x. I'm getting closer and closer to 2, so I can plug in 2 here. And so I got 3 minus 2, which is equal to 1. If it tells me, though, I'm looking at the limit as x is approaching 2 on the right of f of x. Well, if I'm coming in from 2 on the right-hand side, that's telling me my x values are going to be greater than 2. So we're going to use values of x greater than 2. And so notice that tells me values of x greater than 2 that I want to use this third equation. And so I'm going to go in here and I'm going to do direct substitution, but I'm using the third equation. So parentheses wherever I see an x. And let's go in there and replace inside that parentheses where x would have been a 2. So looking at this, this tells me the limit as x approaches 2 from the right-hand side. Without even looking at the graph, I get back also 1. The next part of this question, it's actually kind of like a 3-part A, asks us find f of 2. But what is f of 2? If we look at our piecewise equation, it tells us when x equals 2, we're using this second equation. So f of 2 in our case is also equal to 2. So that actually brings us into, even though our limit exists at x equals 2, our function is actually not continuous at x equals 2. And that will bring us into a little bit later this week. That's how we show that a function is discontinuous at a value. We'll get more in detail again about that next week. Not next week, sorry. later this week. Okay, let's just look at one more side. Actually, that was it, I think. Does the limit as x approaches 2 of f of x exist? Why or why not? Well, recall, in order for a limit to exist, the left-hand side has to equal the right-hand side. Our left-hand side, we got back 1. Our right-hand side, we got back 1. And so the answer to that question would be yes, it does exist. And the reasoning is because the left equals the right. So limit as x approaches 2 on the left of f of x equals the limit as x approaches 2 on the right of f of x. What if, just really quick, if it looked at the limit as x approaches 1? On the left. If that's not an endpoint of our inequality, then we don't really have to worry about which equation we're using for the left and the right. In this case, x is less than 1 would always hold for x is less than 2, right? And so I can see here that that limit is going to be the exact same thing as my limit as x approaches 1 on the right-hand side, because I'm looking at values just a little bit to the right, like 1.1 or 1.2. So that's still less than 2, which is going to be equal to the limit, and it's going to exist as x approaches 1. Let's just even go further, of f of x. So we're just going to go into this first equation, and wherever we see an x, we're going to replace it with 1. So this is 3 minus 1, which in this case is equal to 2. So if you're looking at limits of a piecewise equation, really the only pieces you have to be careful of is when the inequality changes, our equation changes. The other thing that we had seen is if our domain doesn't include something to the left or the right of our x values, then we would have just a one-sided limit, and that is okay. So we're going to stop here. And I apologize because as I closed that screen, I didn't get that one message about enabling the transcription. So you can always go back and watch these once I have uploaded them, because I upload them to YouTube, and then they do the closed captioning, and they should be really good with hopefully doing that. Okay, so let me stop the video.